Thank you very much. Today I will be talking to you about Mechanophotonics, this field which we developed in our laboratory, and this gives guidelines to use crystals and how one can manipulate them to fabricate photonic integrated circuits. Before going to my talk, I usually, not have enough time to acknowledge the people, so I acknowledge the people who contributed for this work, my former PhD students, postdocs, and the collaborators, and the funding agencies. Mechanophotonics is a discipline which comprises of two major fields, mechanical manipulation and nanophotonics. I will discuss to you about mechanical manipulation after a couple of slides. Let me introduce what is nanophotonics. Nanophotonics is the study of behavior of light on the nanometer scale and how the light interacts with the nanoscale objects. So the interaction of the light with the nanoscale objects are completely different when you compare with the bulk materials. And that is what we are going to see in today's discussion. So what is light? We all know light is an electromagnetic wave which propagates approximately 186 miles per second. That's the speed of light, and the light composed of oscillating electric and magnetic field, which are perpendicular to the propagation direction, and the oscillation frequency determines the energy of the light. And if you look at this image, you are seeing various colors which are visible to our eyes, which is ranging from 400 nanometer to 700 nanometer. In photonics, mostly the visible light and infrared radiations are used. Near IR, far IR, mid IR range infrared radiations are also used. And so it's very important to understand how this speed of light is connected to the material's properties. If you look at this beautiful equation emerged out of James Clerk Maxwell's four beautiful equation, the last equation connects the velocity, speed of light, with the magnetic permeability and electric permittivity of the medium. In this case, it in vacuum is given. And so the speed of light in a medium and determines the refractive index. So the ratio of the speed of light in vacuum and the speed of light in a medium determines the refractive index. And for a non-magnetic material, the refractive index N is related to dielectric permittivity, which we call dielectric constant. And also it's connected to another very important parameter called chi, electric susceptibility. And this chi determines whether the material is linear material or optically non-linear material. And so refractive index is very, very important requirement for photonic materials. And if you look at here, the two different media given here, N2 equal to 1, which is air, and N1 equal to 1.4, you can consider this a kind of organic medium. And so according to Snell's law, the refractive index gives a critical angle, which is 41 degrees. So when we launch a light greater than the critical angle, total inner reflection occurs. And if you look at during the reflection, some part of the field goes out to the rarer medium, and its amplitude decays exponentially when it goes away from the surface. This is called evanescent wave or a field, which is very, very important in photonics because this is used to couple two optical components. And if you look at photonic integrated circuits, these are all very small micro devices, and it has many functions depending upon the kind of photonic components you put together, and it's almost very much similar to electronic integrated circuits. In this case, photonic integrated circuits use photons, whereas the electronic integrated circuits use electrons. It's much smaller and faster in comparison to the electronic integrated circuits, and useful for many advanced technologies like quantum information processing, sensing, and LIDAR is emerging sensing field and communication technologies. So it is expected that by the end of 2031, the revenue in PICS business will reach up to $8 billion US dollars. Mostly silicon-based, silicon and silicon-based compounds and main group elements are used for PICS fabrication. Silicon has many advantages like high refractive index and CMOS compatibility during the fabrication process, but it also has some drawbacks like post-fabrication rigidity, passivity, and high thermo-optical coefficient. And silicon is a centrosemitic material, so we can't expect any second harmonic generation. And we have multi-photon emission, but those properties are quite weak for silicon-based materials. So this warrant us to search for a new material. So organic crystals is very important material to be explored for photonic applications and filling the potential gaps and also taking the advantage of silicon-based materials. If you look at a PIC, a single PIC, indium phosphide-based PIC is shown here. It consists of many complex circuits and components. Their connectivity decides the functionality. And if you look at this picture, you can see many components are given here, and waveguides, bend waveguides, ring resonators, splitters, delay lines, and interferometers, and splitters, and odd-on drop filters. So if you see these structures, you can immediately wonder how the crystals can be bent, because we know that crystals are usually brittle, and creating a bend circuits need bendable crystals, so-called flexible crystals. And the flexible crystals is not the only requirement. It also should possess optical attributes, okay, and optical transparency and active or passive waveguiding property it should possess. The first flexible active waveguide was reported in 2005 by Takasawa Group, and in 2013 we reported passive waveguides. And the detailed understanding of the structural bases which are responsible for the crystal flexibility, if you want to refer, you can look at these papers published by Professor Desiraju and Malla Reddy's in the same time where this optical waveguides published. And these elementary waveguide structures are very important. They are the spine for many optical devices such as interferometers, couplers, polarization converter, and ring resonators, etc. And if you see a ring resonator, you have to bend a crystal to make a ring. Yeah, and the circumference of the light is of the resonator is very important. If the circumference of the resonator is integral multiple of the wavelength of light, and then there is a phase matching condition, and you will have a multiple round trip of the light happening inside the resonator. Okay, so this essentially causes optical interference, and when you have a constructive interference, so you will have optical modes, and destructive interference, you won't see any signal. And as a chemist, you can see that the crystal's chi, which I discussed with you before, can be changed. The order of the chi can be 1, 2, 3. So depending upon the symmetry and the kind of donor acceptor compound one choose, one can play around with this chi also, which is not possible with the silicon photonics. An example of organic resonator is shown here, and it's a donor acceptor molecule. And you can see beautiful optical interference is shown here. And the Q factor is around 900, which we calculate using the tallest peak over here. And this is the FTDT numerical calculation for one of the modes appearing at 642. And it shows that the electric field is situated at the interface between the material and the air medium. And also the Poynting vector gives an idea about which direction the optical energy is scattered. And in this material, we were also able to record the second harmonic generation, which shows that the packing of the molecules is non-centrosymmetric, and we also have recorded two photon luminescence as well. And so for the last 10 years or so, we have published several resonators. I'm not going to discuss, but the resonators also can be chiral. So one can incorporate circular dichroism also in the NLO signals. So organic crystals have very interesting property and gives lots of opportunity for us to exploit on them for the photonic integrated circuits. And so if you look at the flexible macro crystal waveguide, and I'm saying it's macro crystal just because the scale is 5 millimeter here, so it's roughly 15 millimeter long crystal and quite flexible. Okay, when you use a pair of tweezers to bend a straight crystal. And what is the reason why this crystal taking this kind of stress and bends? If you look at the molecular picture, you have various interaction like a pi-pi, CH-pi interaction and hydrogen bonding interaction. So if you can consider the pi-pi interaction kind of a spring, okay? So when you try to bend a crystal and the molecules compress in the concave portion and the molecules pi-pi stacking distance increases in the convex part of it. And this is quite reversible. But to fabricate photonic integrated circuits, we can't use millimeter-sized crystals, and also we can't use a pair of tweezers because the circuit is in micro domain, and we have to use microcrystal, and you need to have a special technique to manipulate microcrystals. In other words, you have to use micro manipulation techniques. And if you look at a macrocrystal, which is elastic, as shown in this video, and the same crystal, microcrystal, deposited on the substrate, behaving almost like a pseudoplastic. Okay, so which shows that the property of the crystal in the micro domain is completely different from the macro domain, and this is because of the adherence force between the crystal and the substrate is quite higher. So it is much higher than the shape regaining energy. That's the reason it behaves like a pseudoplastic. So this is the turning point in our research. So we thought that because of the pseudoplasticity and behavior of the crystal, we can use them for a peak fabrication, and that is the starting point for this mechanophotonics. So what actually the mechanophotonics, this is a discipline that uses mechanical macromanipulation of single crystal optical components to advance nanophotonics, such as one can fabricate crystal-based microscale organic photonic integrated circuits. So this is the essence of mechanophotonics. And so the manipulation is not quite simple. This we have been working on for a long time, from 2014. Crystal lifting using AFM cantilever, cutting, bending to create ring resonators, and also slicing of the crystals, and putting two crystals together and aligning them, integrating them to create circuits, and also transferring a new crystal from one substrate to another substrate and integrating them. So these are all several techniques one need to employ to create optical circuits. So if you want to create an optical circuit, you need to know a required function, and then you need to have an idea. So one should really think how we are going to get this function. So once you have the idea, you have to decide whether you want to have a monolithic circuit or hybrid circuit. So then you go here, you have a crystals, and you select the crystals. You want to cut them of a required dimension, you cut it or you slice it. If you don't want to do it, you lift it and release it at a substrate where you want to construct a peak. So once you released the crystal on the substrate site, then you start bending it, and aligning and integration can be done. Finally, you produce a monolithic organic photon integrated circuit. And if you want to hybrid, a bit challenging because two different crystals are having different electronic properties have to be placed in this construction site. Okay, and then that is a time-consuming process. But these are all proof of principle experiments which you want to demonstrate here, which results in hybrid organic photon integrated circuits. An example is shown here. So where we use optical waveguide to create this kind of 2x2 directional coupler, which is acting as a beam splitter. A beam splitter is one which splits the light signal into two beams at 90-degree angle. So exactly this is what happening here, but the angle is different. And if you look at here, this directional coupler have different optical path lengths, and so one of the path lengths is shown here. This is 66 micron. The other one is 90 micron. And when you shine a light, that is input light, the light travels around this crystal, and majority of the light outcouples at this point. And evanescently, some of the lights also coupled here, and then it also outcouples at this point. Okay, and there is no light outcouple at this point, which shows that the directional coupling behavior of this particular circuit, and the light splitting actually happens in organic crystals. The function which are incorporated in the circuits are passive function, because the fluorescent light is coupled here, and it propagates, and there is a reabsorption also happening. If you look at here, there is a reabsorption, so the bandwidth also changes. Once it evanescently coupled to the neighboring crystal, what happens is the light is passively goes here. So we have active and passive and bandwidth alteration also happening. And these are the mechanisms one can incorporate in organic peaks. And if you see here, in this particular case, we had a kind of ambitious project of creating a ring-shaped crystal, okay? And so that we can use them for a ring resonator. And eventually, the idea is to create a integrated 4-port photonic circuit. And if you look at here, this is the cartoon diagram, and you can see the finely constructed circuit, the electron microscope image, and the circuit is quite stable even under experimental condition. Electron microscope is quite stable, and you have 4 ports, 1, 2, 3, and 4, and 2 waveguides. The first waveguide is made into a ring resonator, and then you have optical waveguide 2, and then optical waveguide 3. And the functions are here: passive, active, and reabsorption. Here we also incorporated one more function, frequency filtering. Okay, and so when you give an input at port 4, the light goes straight, and reabsorption happens. So the outcoupled signal is now labeled as -1, and the light also coupled to the ring resonator, and you have. So if you look at the optical spectrum, we have also modes, and these modes are different when you before coupling and after coupling. So the optical waveguide 3, before integrating with this ring resonator, has different modes, and after coupling it has different mode. This shows that the frequency filtering also can happen. So we also created this kind of hybrid circuit using 2 different crystals. And if you look at here, this is the way we construct the circuit, and the final circuit is quite stable under electron microscopy experimental condition. And the table looks pretty complex here, but what I want to tell you is we were able to incorporate passive, active, in this case, energy transfer also. So the energy transfer happening between this crystal and this crystal, because they are electronically different. There is a overlap between the emission of one crystal with the absorption on another crystal, and thereby we can specifically control the output. Here it is 0, T3, there is no signal is coming out when you try to give an input at T1. And so similarly, you can add one more column by putting one more optical component over here, and thereby you can control the signal output, whether you need to have 1 or -1 or 0, or which direction also you want to launch. That also can be done using reconfiguration. So the programmable OPICs are emerging area, okay, not yet realized. So in order for us to realize programmable OPICs, reconfigurability is a very, very important point. And that is what we have demonstrated in this particular experiment. And this is the last slide. What it shows is the light output also can be changed around this substrate at various angle. And what we have done is we have incorporated around 6 signals, okay, of different bandwidths. And the functions are active and passive type, but the bandwidths are different. And if you look at here, this is when you excite at port 1, and this is the signal output you are getting at port 2, 3, and 4. But now what I want to do is I want to change this port to direction, and I change it mechanically to 185, thereby the same signal but emitting a different direction. Similarly, 345 can be changed to 330, and 195 also can be changed to 208. Thereby, we have demonstrated that you can steer the optical signal, complex signal. 6 signals can be steered around the substrate using mechanical reconfigurability. And in summary, so the organic crystals are new material platform for nanophotonic components, and reconfigurable organic photon integrated circuits are really emerging. And Mechanophotonics is a new tool to micromanipulate flexible optical crystals towards OPIC, and OPIC is itself a new research direction. Thank you for your attention.
Thank you very much, Professor Chandrasekar. I'm just looking to see if there are questions in the chat. There is a question to you from G. Bhaskaran. It says, degradation seems to be a challenge in organics-based electronics and photonics. How do you address this problem?
See, this is a valid question. So if you want to avoid this, we have to go for embedding the whole circuit, and we have been working on. In fact, this process is already there in electronic circuit. That is called embedded circuits. So one can embed the circuit with low refractive index polymer film. Thereby, one can stabilize the optical circuits and avoid degradation.
Okay, there's another question to you from Shubhra Anantakrishnan. The question is, how do you join the ends of a ring resonator?
That is very challenging. So one need to have good patience, and that is the only thing I can say. And precision. So these are a precision micro manipulation technique. One should pay attention while fabricating the circuits and joining the ends. And the ends need not to face each other. It can just, one can connect the edges of the two ends. That's also okay. Essentially, what is necessary is the light should circulate around the ring. That's a good question.
Right. Maybe I could ask a follow-up question to that. So yes, considering that so much precision is required and perhaps the chance of success, I don't know how much that would be, would this be amenable then to robotics manipulations?
Yes, madam. Actually, this is a proof of principle experiments. We are not claiming that the technology which we develop in our laboratory can be directly transferred to industry. That is not possible. These are proof of principle techniques. And as you exactly said, automation is needed, and that is highly possible.
Right. There's one more question to you from E. Arunan. The waveguides you discussed had micron wavelengths. If I remember, is it possible to have it for centimeters?
See, usually when you have in centimeters, what is happening is you have lots of defects in the crystals also. And the shapes and the surface smoothness all will be different when you compare the crystal. Millimeter size crystals are known, but centimeters also there. Yeah, we have done it. But the point is, you can't trap the light, and more importantly, when you have centimeter size crystal, the thickness also will be very, very important. Thick crystals are not suitable for bending it to create optical resonator. So we usually prefer thin crystals of micron length, and because the device requirement also the micron size. So we can't use directly centimeter sized crystals to make a photonic integrated circuit. Then it will look really huge. And so this is one point of many problems.
I don't think there are any other questions. So with that, thank you very much for a very interesting presentation.